All right, this next example, example 6. Here we are going to do a u substitution before we do anything else. So here we can start off with letting u equal, we can do natural log of x. The reason why we would want to choose that is because the derivative of natural log of x is 1 over x, and we do have a 1 over x right here, so that would work out. So this would become 1 over, the 1 over x goes away, so that 1 over x dx becomes a du, and then this would become the square root of 4 minus u squared. We would change our bounds as well. Our bounds would turn into u of 1 is natural log of 1, which is 0, and u of e is natural log of e, which is 1, so 0 to 1. Then we can do a trig sub. So for the trig sub, we would let u equal 2 sine theta. So then we have a du equals 2 cosine theta d theta. And then we could solve this u equals equation for theta, so creating a function theta of u, a function of u. So theta is the sine inverse of u over 2. So the lower bound, 0, so theta of 0 is the sine inverse of 0, which is 0. And then theta of 1 is the sine inverse of sine inverse of 1/2. I'm sorry, of 1/2 this would be. So we're looking for, remember that sine inverse spits out angles on the right half of the unit circle from negative pi over 2 to positive pi over 2. And the sine of an angle on the unit circle corresponds to the y value of that point. So we're looking for a point where the y value is 1/2. Well, that would be right here. I guess it's not drawn to scale. If I draw this to scale, y equals 1/2 would be somewhere right here. In which case, this angle here would be pi over 6. So sine inverse of pi over 2 is, or excuse me, a sine inverse of 1/2 is pi over 6. All right. So all of that taken care of, we can now use this to rewrite our given integral. So this integral here would become the integral from 0 to pi over 6. The du becomes a 2 cosine theta d theta. And then the bottom, we have the square root of 4 minus 4 sine squared theta. Of course, this becomes the square root of 4 cosine squared theta, which that, of course, simplifies to 2 cosine theta. And the 2 cosine thetas actually cancel each other out completely. So this is the integral from 0 to pi over 6 d theta, which is theta between 0 and pi over 6, which is just pi over 6. All right, so next we'll take a look at example 7. And this one's just going to be a direct substitution. So although trig sub is very neat and it works well, it is it's a very specific technique of integration. And it's more sophisticated. Something like a substitution method, like a u sub, that has a fairly general applicability, whereas integration by parts, it's still very general, but maybe a little bit more specific. Trig sub, even more specific. Generally speaking, when you approach a problem, you want to start with the most general, easiest to use method, but if those don't work, then you have to find yourself honing in on a very specific method. So although trig sub is valid to use here, it's not what you would want to use. A basic u sub is way easier. Let u equal 1 minus x squared. then du is minus 2x dx. We have an x dx, but we don't have a negative 2, so I'll divide that over. So then this would become negative 1/2 the integral. The x dx goes away to give the negative 1/2 du, which we have, and this would be the square root of 1 minus u squared. Or excuse me, this would just be the square root of u. Or, written differently, this is the integral of u to the negative 1/2 du. So if we add 1 to the exponent, we'll get positive 1/2. So u to the positive 1/2 plus c, and then we divide by positive 1/2. So 2. So this is negative the square root of u plus c, which is negative the square root of 1 minus x squared plus c. Very easy, but also, yeah, let's just keep it at that. It's straightforward, it's easy, it's quick. That's what you should do. Trig sub does work. So as I trig sub works, but it's harder. And maybe you don't think of it as harder. There's certainly more to do with it. And that alone is enough to not want to pursue it. But it would work. You would let x, in this case, equal, what do we have here? This would be sine of x. Or sorry, sine of theta. So then dx is the cosine theta d theta. So then this whole integral, x over the square root of 1 minus x squared dx, this would become the integral. So the x becomes a sine of theta, the dx becomes a cosine theta d theta, and then the inside of the square root becomes 1 minus sine squared theta. Again, the square root becomes a square root of cosine squared theta, which is just cosine theta, and then the cosine theta in the bottom cancels with the cosine theta in the top, and then you're left with the integral of sine of theta. Now so far this is pretty straightforward, it's not that hard. The antiderivative of sine is negative cosine theta, and we got a plus c. But now you've got to go ahead and, using your substitution here, construct a triangle that corresponds to it. So sine is the ratio opposite over hypotenuse. So we can write x as a ratio, x over 1, so opposite over hypotenuse, and then the adjacent side length, using Pythagorean, would be square root of 1 minus x squared. So then you can say that from here, the cosine of theta is the adjacent side length over the hypotenuse. So importing that here, we have negative the square root of 1 minus x squared plus c. This one didn't turn out to be that bad. So, you know, take your pick. Both work. But generally speaking, if you have a choice between a trig sub or a u sub, usually the u substitution is what you want to go with in general. But again, in some examples, the difference in the number of steps or what you have to do is, could be a lot, could be a big difference, could be not that much of a difference. Okay, let's include example 8 in here. So this example 8, for this one, we can certainly do a straight up trig sub. A u sub might also work. Let's try that first. So if we let u equal, let's let u equal t squared plus 2. But then what happens here, our du is a 2t, so that's not going to be great. Okay. What if we let u equal, I guess u sub that, I guess that won't work that well. We can try something else. Let's see, what if we go ahead and write t squared over the square root of t squared plus 2, What if we write that as t squared plus 2 minus 2 all over the square root of t squared plus 2? I'm not sure if this will lend us anything fruitful. Perhaps it will, perhaps it won't. So here, if we rewrite this, simplifying, we have this. Is this any easier? Is this any easier? Don't think so. All right. This format here that the given integral was in, to me, it definitely speaks of a couple different integration techniques, both of which I tried, just maybe rearranging this, maybe adding to, subtracting to, and splitting the fraction. Sometimes that can yield some fruitful results, and they're fairly quick to just kind of write down and chicken scratch and think about. That's always a good idea when you're doing when you're approaching a new integral and you're not 100% certain on the technique you should use. Spend 30 seconds just thinking about the other possibilities. All right, so we've done that, and I definitely think that this one, trig sub, is the way to go, it seems. So in this case, we would let t equal the square root of 2 tangent of theta. So then dt is root 2 secant squared theta d theta. So this would become the integral. The t squared in the numerator becomes a 2 tan squared theta. And then the dt becomes a square root of 2 secant squared theta d theta. In the bottom square root, we have 2 tangent squared theta plus 2, which of course the square root simplifies into 2 secant squared theta, which simplifies into the square root of 2 times the secant of theta. And then, let's see here, the root 2's cancel, and then one of our secants cancels. So we now only have one secant term in the numerator. Okay, so pull out our constant of 2, and then we have tangent squared theta secant theta d theta. Okay, so let's see here. Thinking u sub, of course for a u sub there's a couple choices. One choice is let u equal tangent of theta, but when we differentiate this we would get a secant squared theta d theta, and we don't have a secant squared anymore. So I wouldn't do a u sub on tangent. Now you could think about, what about letting u equal the secant of theta? Then du is secant theta tangent theta, which, since we do have two tangents of theta, we could split this into tan theta, secant theta, and then these two would become the du, but then we would have this tan theta left over. And there's not a nice way to get this looking like a tan theta. Well, there is. There's a little step here you'd have to take, though. You can square this to get u squared equals secant squared theta, and then we could subtract 1 from each side. And then secant squared theta minus 1 is tangent squared theta. But again, we only have one tangent, so that's not great. Okay, so those are all great thoughts to have, to think through the various methods that you could employ here. What I'm going to do is I'm going to change this tan squared theta into a secant squared theta minus 1. And then I'm going to distribute this secant through so that we have the integral of secant cubed minus the integral of secant of theta. And these are two given integrals. So as a reminder here, do this up here since we're not going to have a ton of room. Actually, I'll do it down here. So some facts. Recall that the integral of secant cubed theta, d theta, this is 1/2 secant theta times tangent theta plus the natural log absolute secant theta plus tangent theta on the inside, plus c. And then the integral of secant, just secant, to the first power, d theta, this is natural log absolute secant theta plus tangent theta plus c. So really it's just this term right here. Okay. So if we go ahead and use that now, we'll move up here to this line, equals 2, and then we've got these two antiderivatives to import. So the one is 1/2 secant theta tangent theta plus natural log absolute secant theta plus tangent theta. Okay, close that off. That's the inner set of brackets. Plus, oh, I do have room over there. Plus the other one. Or so not plus, was it minus? It's minus. So this is minus natural log absolute secant theta plus tangent theta. All right, distribute the 2 from the outside all the way in. So this would free this term, these two terms up. So secant theta tangent theta plus natural log absolute secant theta tangent theta, plus tangent theta, I should say, minus, and this becomes a minus 2 natural log secant theta plus tangent theta. And I should have a plus c there and there. Ooh, okay. So then we got some like terms. So this is secant theta tangent theta minus natural log absolute secant theta plus tangent theta plus c. All right, we want to use our triangle. So let's, over here, we can draw a triangle. So we'll go ahead and solve this for tan theta, which will give us a t over root 2. So this tells us the opposite is t and the adjacent is square root of 2. So on a right triangle that we'll just sketch, relative to this angle theta, the opposite is t, adjacent is root 2. So this should be t squared plus 2 when we use the Pythagorean. So we need secant. Secant of theta is the ratio. Well, it's the reciprocal of the ratio for cosine. Cosine is adjacent over hypotenuse. So for secant, it's just the flip of that, the reciprocal of that. So secant is the hypotenuse over the adjacent. So secant of theta is this square root of t squared plus 2 all over the adjacent side length of square root of 2. Okay, so we know what tangent of theta is. It's t over root 2, and secant of theta is the square root of t squared plus 2 over root 2. Okay, so secant of theta times tangent of theta, and we multiply them together. Our root 2's in the bottom should combine to give us a 2, and then multiplying the numerators, we'll have t times the square root of t squared plus 2 minus the natural log, and then we have common denominators, so square root of 2, and then secant here we will have the square root of t squared plus 2 plus t for tangent of theta. So that one was a little bit of work. But there you go. And again, you should always be able to differentiate here and to test it, to double check that this is correct. So if we go ahead and differentiate this, which I will pause for since it's lengthy. All right, so that derivative does check out, but that took a while to do. That is a really good exercise in derivatives and algebra to get this to fall out at the end. But yeah, you can always check your work. All right, in this last example, this video encompasses some harder examples. So let's take a look at this one. So for this one, it might be possible to do a U substitution now that I'm looking at it. I'm not entirely sure if that is true or possible, but it looks like it may be possible. We would probably try let u equal 9x squared minus 1. Then du is 18x dx. All right, let's just try let u equal x squared. Let's try that first. If we let u equal x squared, then du is 2x dx. And I'm going to do something I don't normally do. I'm going to just solve for dx so that we have 1 over 2x du. And then I am going to, let's see here. So in this integral, we have the square root, which would become just 9u squared minus 1. Okay. And then our dx becomes a 1 over 2x du. And then don't forget, we have this x cubed here we haven't yet dealt with. So we've got this x cubed in the bottom here. Well, notice that if I group my x cubed in the bottom with this x in the bottom, right, that's going to make an x to the fourth. And x to the fourth is just u squared. Square this equation. So then the 1/2 is free to move out. And then this would be a 1 over u squared in the bottom. Okay. That is pretty strange. But now that we have this, is this actually any easier? Well, a little bit. How much more? I'm not sure. Could we do another substitution? Let w equal 9u squared minus 1. Then dw is 18u du. Okay. That doesn't look like it will hold up nicely, unfortunately. Yeah, I don't really see a nice way to go about that one. Yeah. I thought perhaps a clever U-sub might simplify it a little bit more. Let's just go at it from the perspective of trig sub. So from trig sub, we can let x equal 1 over 3, so 1/3 secant theta. So then dx is 1/3 secant theta tangent theta, d theta. So then this would become the integral of, so the dx, so 1 in the top, but then times dx. So we have a 1/3 secant theta tangent theta, d theta. And then the bottom, the x cubed will become a 1 over 3 cubed, so 1/27th secant cubed theta. And then we're going to need a much bigger fraction here, so let's just move this over a bit. And then here on the inside, the 1/3 when it gets squared will give us a 1/9, which will cancel with that 9th. So we should be left over with the secant squared theta minus 1. So then dividing by a fraction, that's multiplying by the reciprocal. So we have 27 over 3. And then here, of course, we didn't actually do our usual method here. Let's first say what this square root is. This is the square root of tangent squared theta, which is just tangent of theta. So it looks like our tangents are gone, and then one copy of our secant is gone. So this is 1 over secant squared theta d theta in the bottom, which 27 divided by 3 is 9, and then secant in the bottom is cosine in the top. So this is cosine squared theta d theta. And cosine squared of theta, we can use the half angle identity, which says that the cosine squared of something is 1 plus the cosine of double that thing over 2, or written a little differently, you can factor the 2 out front and write it like that. So we'll use that identity here. So this will be 9 halves. We'll collect our fractions. The integral of 1 plus cosine of 2 theta d theta. So integrating this, we'll have a theta plus 1/2 sine theta plus c. So multiplying that out, 9 halves theta plus 9/4 sine theta. Oops, sorry, not sine theta, sine 2 theta. All right. There is the double angle identity for sine, and that is sine of 2 theta is just 2 times the sine of theta times the cosine of theta. So why would we want to do that? Why do we care? Well, because this is not a definite integral, we are going to have to go back to x's, right? Yep, x's are a variable. We have to go back to x's. And in order to go back to x's, we need to draw a triangle. That's what we've done in all the previous problems. So if we draw a triangle based on our initial trig substitution, this equation, secant of theta equals 3x, therefore cosine of theta equals 1 over 3x. When you draw this triangle, the argument of cosine is theta. So when we draw this, we're drawing a theta triangle. Not a 2 theta triangle. So because this argument here is 2 theta, we can't expect the conclusions we would draw from applying SOHCAHTOA and Pythagorean to this triangle to apply to 2 theta. So we use the double angle identity so that we now have trig functions that are all in terms of theta, not 2 theta. So then this triangle that we can draw in a moment will actually link up correctly. So cosine of theta is adjacent over hypotenuse. So adjacent is going to be 1, hypotenuse is 3x. So this side length here is 9x squared minus 1 via Pythagorean. So the sine of theta is the opposite side length over the hypotenuse, 3x. Okay, so we've got our cosine, we've got our sine, which is great. I'll take care of these 2 terms. But what about this theta? Well, if you have a theta, there's only one way to write theta, not in terms of a trig function. Well, actually, let me rephrase that. There's only one way you can exchange this theta for an x, and that is it has to be in terms of an inverse trig function. So from this, we could actually just use any number of these different relations. Doesn't matter how you want to do it. I would probably just go with cosine. Cosine inverse. So theta equals the cosine inverse of 1 over 3x, but you could have also said theta is the secant inverse of 3x. I don't care. Either one of these is a fine choice. Just pick one. This one or that one. So importing all that information, we would have 9/2 cosine inverse of 1 over 3x plus 9/2 the sine of theta is the square root of 9x squared minus 1 over 3x, and the cosine of theta is 1 over 3x plus c. You can clean this up a little bit, but not a ton. So factor the 9/2, which is in common. And then this would become square root of 9x squared minus 1 over 9x squared plus c. And that's as nice as it's going to look.